This is a graphic explanation of the cathodic shielding problem in underground steel pipelines. The overall subject of cathodic protection is extremely complex. The cathodic shielding problem is only one aspect of the cathodic protection field. We have certainly oversimplified our explanation of cathodic protection, but we don't think we have oversimplified the problem of cathodic shielding. Judge for yourself. Below is an underground steel pipeline which we want to protect from corrosion. The first step in protecting the pipeline is to apply a corrosion coating. In this case, we are applying a coating of fusion bond epoxy, FBE. Next, we install a cathodic protection system, which consists of a ground bed of anodes, a rectifier to provide direct current, and a wiring system to connect the anodes, the rectifier, and the pipeline. The cathodic protection system serves as a backup to the corrosion coating system. If the corrosion coating system begins to fail, the cathodic protection system should take over the job of corrosion protection in the area of failure. Now we will activate the cathodic protection. The cathodic protection system sends out direct current, which, since it is searching for a return path, will search out any defect in the corrosion coating through which the current can reach the steel surface of the pipeline. If the corrosion coating is doing its job, defects are not found and very little current is used. However, even the best coatings develop areas of failure after a period of time. Let's look at a typical failure sequence in our fusion bond epoxy. First, an area of the coating becomes disbonded from the surface of the steel pipeline. Next, water enters the area underneath the disbonded coating. Conditions for corrosion activity have now been created. Because an adequate cathodic protection system has been installed, the cathodic protection current, always searching for a return path, discovers the disbonded area. Several studies have proven that fusion bond epoxy coatings allow the passage of cathodic protection currents to disbonded areas. The cathodic protection system now begins its work. Current penetrates the corrosion coating to the pipeline surface, where it can complete its circuit and return to the rectifier. The current changes the pH of the water to a higher or more alkaline level. At higher pH levels, 9 and up, corrosion of steel is minimized. The cathodic protection system is now using more current, but it is doing its job as backup corrosion protection. The example we have just shown is how the system is supposed to work. Fusion bond epoxy is a fail-safe coating. If fusion bond epoxy fails, becomes disbonded, the pipe is still safe because protective current will be able to reach any water under the disbonded area. However, not all pipeline corrosion coatings are fail-safe. Most corrosion coatings with solid film backings have been proven to block passage of protective currents. Now let's say that, instead of the pipe being completely coated with fusion bond epoxy, the girth welds are coated with shrink sleeves. Shrink sleeves utilize a thick and solid film backing, which has a high resistance to electrical current. With solid film-backed coatings, if disbondment occurs and water penetrates under the disbonded area, the cathodic protection current is usually blocked from providing adequate protection. This is because the high electrical resistivity property of solid film backing shields the protective current from the corrosion activity. This means that solid film-backed shrink sleeves, tapes, and 2 or 3 layer systems are not fail-safe. If these coatings fail, become disbonded, the cathodic protection current can be blocked, and its backup protection ability can be limited. If your pipeline is sick or wounded because of disbonded corrosion coatings which shield cathodic protection currents, your pipeline is in danger. Thus far we have seen a coating which is fail-safe and another coating which is not fail-safe. Now let's look at a second fail-safe coating, the Polyguard RD6 coating system. If the girth weld had used RD6 as a corrosion coating, the RD6 would have been applied in a spiral wrap configuration. Although this is a rare event, let's picture the RD6 coating becoming disbonded and water entering the disbonded area. In the case of RD6 coating system, cathodic protection currents have been demonstrated to travel underneath the overlap to reach water in disbonded areas. Polyguard RD6 corrosion coating is a fail-safe coating. If the RD6 coating disbonds, cathodic protection currents can reach water underneath the disbonded area. As with fusion bond epoxy, the pH of the water is changed by the electrochemical process of CP current. The condition of disbondment of corrosion coating, whether it happens under fusion bond epoxy, RD6, or any other high-quality corrosion coating, is almost always caused by improper application. Under normal circumstances, there will be no disbondment, no water will enter through the coating, and no CP current will be used. NACE Standard RPO 169-2002 says that you should not use materials which create electrical shielding on the pipeline. Regulations in 49 CFR 192.461 and 195.551 say that coating materials must have properties which are compatible with any supplemental cathodic protection. Is your organization using fail-safe coatings? If you operate a pipeline and would like to determine if the corrosion coating you use is fail-safe, Polyguard Products has developed a laboratory test which can be used to determine if corrosion coatings are fail-safe. For details, see the technical reference section of the Polyguard website.